In this video, I want to introduce and formalize big O notation. If you've taken data structures, you may have encountered big O notation as a way of describing the running time of different algorithms. But mathematically speaking, big O notation is about describing the growth rate of functions. And so when we talk about algorithms having certain big O complexity, what we mean is that the function describing the algorithm's runtime relative to its input size has a particular growth rate. So if we're asking the question of how fast does a particular function grow, a useful approach is to compare it with other functions that we're more familiar with. If we compare the growth rate of different functions, we might say that the function g of x equals 5x grows faster than the function f of x equals 3x. But the difference between these two linear functions pales in comparison to the difference between a linear function and a quadratic function. If I add the function h of x equals x squared and then rescale the axes, as the input grows, the quadratic function completely dwarfs the linear functions, and the difference between those linear functions seems quite small. Whereas the difference between two quadratic functions with different constants is much less dramatic. If we add a cubic function to our graph and zoom out again, we find that either of the quadratic functions is just as dwarfed by the cubic as the linear functions were by x squared. And again, two cubic functions with different constants look much more like each other than they do like quadratic or linear functions. So big O and related notations give us a way of comparing the growth rate of different functions, which then lets us classify different types of functions that grow similarly versus others that grow at a very different rate. So let's go to the whiteboard and talk about the formal definition of big O and related notations. I've now used the phrase big O and related notation several times, and that's because big O is one of a family of related notations. Among this family, big O is the one you will see most frequently because it is most useful for talking about the running time of algorithms, but the others will also turn up from time to time. All of these types of notation are about expressing some relationship between two functions, and the sorts of functions that they apply to are ones that map natural numbers to real numbers. So for any of these, we are talking about the relationship between two functions f and g that have to take a natural number as their input. This works well for expressing running time as a function of input size, because we can always express the size of the input for a particular problem as a natural number. And then the amount of time that the algorithm runs for can be expressed as a non-negative real number. The way that we express relationships between different functions' growth rates is by saying that one function is big O of another. If we say that f is big O of g, then we are saying that f grows no faster than g. We'll be precise about what we mean by grows no faster than in a minute, but we should think of f is big O of g as saying that g gives an upper bound for how fast f can grow. Similarly, big omega expresses a lower bound on the growth rate. If we say that f is big omega of g, then we're saying that g is a lower bound on how fast f can grow because f grows no slower than g. Big theta is a combination of big O and big omega. If f and g grow at the same rate, then we can say that f is big theta of g, and we can also say that g is big theta of f. Little o and little omega are making stronger statements than big O and big omega. If we say that f is little o of g, then we are saying that f grows slower than g. Big O allows for the possibility that f and g grow at a similar rate, but little o does not. If f is little o of g, we're saying that f is definitely growing slower. And likewise, we say that f is little omega of g if it grows much faster. So now that we have a sense of what kind of relationship the notation is trying to express, let's be precise about defining those relationships. We define big O as applying to functions that output real numbers when given inputs that are natural numbers, so these types of functions. And when we're saying that f is big O of g, we are, broadly speaking, saying that f is upper bounded by g, so that if we apply f and g to the same natural number n, we will get a smaller result from f than from g, but we are allowing for a lot of wiggle room here. We're not saying that f always gives a smaller output. First, because we have this constant multiple, m, so we're saying that f gives a smaller output than m times g. So it might be that m is 100, and so we could be saying that f is less than or equal to 100 times g. And if there exists any such constant, then we can have this relationship. And we also have wiggle room in that there can be finitely many exceptions. We could have that f of n is larger for some inputs, even if we choose a really big constant. But we're saying that the number of cases where f is bigger is finite, and so if we go out far enough on the number line, we will eventually get to a point where from there to infinity, m times g will always be at least as big as f. So let's illustrate this with some examples. For this f and g, we know that for any natural number other than 0 that we give as input, f will actually give us a larger output than g does. But we can prove that f is big O of g by giving some constant m that we can multiply by g in order to make it at least as large. If we choose m to be 2, then when we take 2 times g of x, we get 6x, and so 5x is less than or equal to 6x for, in fact, every natural number x. And so since there are 0 exceptions, we have a finite number of exceptions, which means that f is big O of g. If we change f to be 5x plus 10, we can still show that f is big O of g, and we can still use m equal to 2, but now we have some exceptions. When we multiply g of x by 2, we get an inequality that will hold as long as x is greater than or equal to 10. So in this case, we have some exceptions to m times g being larger, namely on inputs 0 through 9, m times g is not larger, But since 0 through 9 are the only exceptions, and from input of 10 on out through infinity, m times g of x is larger, we have finitely many exceptions, and so we can say that f is big O of g. For these cases, I hopefully don't need to do a lot to convince you that m times g will always be larger. But in some cases, the relationship between f and m times g is less obvious, and so we would need to prove this relationship. You've seen a number of examples recently where we've proved an inequality relationship between two functions using induction. And so, if it's not immediately obvious that m times g is always at least as large as f, then we would need to prove this step, and we would most often do that with a proof by induction. Here we can use 3 as our value of m. And again, we have a case where for small inputs, 3 times g will not actually be larger than f. So our goal is to find the threshold beyond which m times g becomes larger. If we can find an intersection between f and 3 times g, then we know that beyond that intersection, 3 times g will always be larger. So having solved for the point where f and 3 times g cross, we now know that the only exceptions where f is larger than m times g should be inputs 0 through 4. And from an input of 5 on out to infinity, 3 times g will always be at least as large as f, and so f is big O of g. We could compare the function 2 to the x with the function x factorial, and even with a constant m equals 1, we can show that g grows faster than f. And we're allowed finitely many exceptions, so it's okay that 2 to the third is bigger than 3 factorial. But when we get to 4 factorial, which is 24, that's larger than 2 to the fourth, which is 16. And from 4 to infinity, x factorial will be larger than 2 to the x. But perhaps you're not convinced, in which case you should prove this fact by induction. Your base case could be x equals 4, and then you can show that if the factorial is larger for x, then the factorial will also be larger for x plus 1. And that's because going from x to x plus 1 multiplies by 2 for f, and multiplies by x for g, and so x is definitely larger than 2 for all of the natural numbers greater than or equal to 4. So in all of these cases, we can say that f is big O of g, meaning that f grows no faster than g, except for finitely many exceptions and a multiplicative constant. If we want to think about a function that grows no slower than another function, then our definition for big omega is remarkably similar. For big O, we were saying that g was an upper bound on how fast f could grow. For big omega, we're saying that g is a lower bound on how fast f can grow. So we are saying that there is some multiple that we can apply to g such that f is always at least as large with finitely many exceptions. And so showing big omega is in fact very similar to showing big O. And so let's think about these same examples and determine whether f is big omega of g. when f is 5x and g is 3x, we want to show that f is always at least as large as some multiple of g. So let's make that multiple of g just be 1, and then 5x should be larger than 3x. And so in this case, f is both big O of g and big omega of g. In this case, well, again, f is already larger than g, so we could choose m equals 1. And in fact, for all natural numbers x, we have that 5x plus 10 is at least 3x. And here again, f is already larger than g, so we could choose m equals 1. And so, for all three of these cases, since f is both big O of g and big omega of g, we can conclude that f and g grow at the same rate. But here, we can't choose m equals 1, because if m equals 1, it's definitely not going to be the case that f of x will stay larger than g of x. Since we're trying to make f larger than m times g, we can give ourselves a lot of wiggle room by making g very, very small. So if we divide x factorial by 100, will that be smaller than 2 to the x? Well, it will be smaller for a few more terms, but if you evaluate 1 over 100 times 10 factorial and 2 to the 10th, you'll find that 1 over 100 times 10 factorial is much, much larger. And in fact, you could prove that for any fixed m that you choose, if you make the input x large enough, it will eventually become the case that x factorial is bigger than 2 to the x. And so if you showed that there was no fixed m we could pick, then you would have proven that f is not big omega of g. For these first three examples, we saw that f was big O of g, and f was also big omega of g. And so we see that it's possible for f to both grow no faster than and grow no slower than g. And so this corresponds to our case of grows at the same rate as, and this is in fact exactly how we define big theta. We say that f is big theta of g if it meets the criteria for both big O and big omega. In general, we'll need a different value of m to get big O or big omega, and so we can define big theta as having two constants, one that gives us big O and another that gives us big omega. So if f is big theta of g, then we are saying that we can use g as an upper bound on f with one constant, and we can use g as a lower bound on f with another constant. So here we had a lower bound when the constant was 1, and an upper bound when the constant was 3. And so we have that f is big theta of g with a equals 1 giving us a lower bound and b equals 3 giving us an upper bound. Likewise, for examples 2 and 3, since we had both the big O and big omega relationships, we have that f is big theta of g. But for the fourth example, we don't have a big theta relationship because f was not big omega of g. Since there was no m we could pick to make g be a lower bound, there's no a that we could fit into this big theta definition. For little o and little omega, we're trying to talk about stronger differences between the growth rate of functions. And so we need a slightly different type of definition. And we do that in terms of the ratio between f and g evaluated at a given n. If, as n goes off to infinity, g is growing faster than f, then the denominator of this fraction will be growing faster than the numerator, and so this fraction will be getting closer and closer to 0 as n gets larger and larger. So this is saying that the function g grows enough faster than the function f that the limit goes to 0. If we think about our examples, we could take the limit as the input goes to infinity. Here, for any given x, the ratio is 5/3, and so that continues to be the case as x goes off to infinity. And so we say that f is not little o of g because the limit is not 0. Here again, if we take the limit as n goes to infinity, we will get 5/3 because the constant will matter less and less. And so again, f is not little o of g. Here again we have a non-zero limit, and so f is not little o of g. But for the fourth example, the ratio f over g does go to 0 as n goes to infinity. And so f is little o of g. So intuitively we can think of little o as also giving an upper bound. G has to be growing faster than f for this limit to go to 0, but it can't be growing just a little bit faster. For the limit to go to 0, it has to be the case that the gap between g and f is getting wider as n gets larger. For little omega, the definition is similar, except that we want g to be a lower bound for f, so we want f to be larger than g and the gap to be growing. And so that happens if the limit of this ratio is infinity. All of these types of notation signifying relationships between the growth rate of different functions have their uses, but I find that as a computer scientist, if I'm using one of these notations, the vast majority of the time I'm using big O. That's because big O gives us an upper bound on the growth of a function, which makes it easy to talk about how long could it take for an algorithm to run. From time to time, we'll encounter big omega when we're giving a lower bound on some problem or algorithm. And it's often the case when we're talking about big O that we could have talked about big theta instead. In computer science contexts, little o and little omega do appear, but are far less common. And so in our activities and quizzes, we will focus on big O and big omega, and much less on little o and little omega.